Hey, what's up, guys? So I'm going to be going over the worksheet from this week for those who didn't get to go all the way through the worksheet, or if you still have questions, or if you just want to see some of this content again, want to hear me re-explain it, this is for you. So I apologize in advance if I'm sniffling, you know how it be. Okay, so first, I wanted to review what happens when you manipulate different reactions. So if I double a reaction, what happens to delta G is delta G doubles. I don't know what I was about to just say. And then K gets squared. If I reverse a reaction, we do the opposite sign for delta G. So if it's positive, it becomes negative. If it's negative, it becomes positive. K becomes the inverse. And if you add reactions, you add delta G's, and K's you multiply. So that's just a little review, and that is all because delta G equals products minus reactants, and K is equal to products over reactants, where the coefficients for the reaction, become the coefficients for products and reactants, versus for K, they become exponents. So like if I have 2 HCl, like it'd be squared. So yeah. Moving on. So for this one, we have, what is the pOH of a 0.2 molar solution of HI? So HI is a strong acid. So if strong acids, well, first, acids, what do? They donate hydrogens, according to Bronsted-Lowry theory, which is the main one that we're using. And strong acids dissociate completely. So because strong acids dissociate completely, for HI, I'm going to do like a simplified version of a rice table. If our initial is 0.2, our final equilibrium, so I'll just say initial and then equilibrium, then our initial here was 0, 0. Our equilibrium will be 0.2 for both hydrogen and iodine ion. So this is the one that's going to be important. So we take the negative log of 0.2, and that would equal our pH. And I believe that equaled, no, I think it equaled 0.7. I don't actually have my calculator on me. And then we still need to get to pOH. So 14 equals pH plus pOH. So 14 minus 0.7 equals pOH, which is equal to 13.3, which is acidic. A low pH or a high pOH means it's an acidic solution. Yeah. Okay, so let's do number 2 now. What is the pH of a 0.6 molar solution of HNO2? So what's the difference here? We still have an acid because it has this hydrogen that we're going to donate, but HNO2 is a weak acid. So for these, we have to do a rice table because they do not completely dissociate. So here our reaction is HNO2 yields H plus NO2 minus, write my rice. Our initial is 0.6, 0, 0, change minus X plus X plus X. And then because this is a weak acid, I'm going to have mostly acid at equilibrium, not ions, which is different from strong acids where I will have very little. It's essentially 0. I guess I can add that. It's essentially 0. where I don't have very much HI and I mostly just have ions at equilibrium. So that's the difference between strong and weak acids, or one difference. So here I'd have mostly 0.6, approximately XX. So this is, for this reaction, this is the Ka of HNO2, because it's going from an acid to its ions. Oh, sorry, I didn't mean to get text. Okay, and that equals x squared over 0.6. So then we solve for x, and x is equal to our hydrogen ion concentration, because we see that here. So then we do the negative log of that x, and that will equal our pH. I'm not going to do the math out, so don't mind all those messages. We're just talking. Okay, they can stop. I really don't want to start over the recording, so we're just going to keep going. But yeah, like I said, I'm not going to put this into my calculator just because I don't want to waste time. If you're having problems putting stuff into your calculator, let me know. We can work through it. But I want to make sure you guys have like the steps so that you know what to do. Anyway, okay, moving on. Now we need to identify the acid, base, conjugate acid, and conjugate base according to Bronsted-Lowry. So according to Bronsted-Lowry, acids donate hydrogen, bases accept hydrogen. And then our normal bases and acids will be here, and then conjugates will be over here. So we look over here, and I go, okay, what is donating a hydrogen? And H2O is donating a hydrogen because it goes from H2O to OH, and it gives a hydrogen to our cyanide. So cyanide gets that hydrogen, so that's our base, and it turns into HCN, which is our conjugate acid, and this is our conjugate base. Sorry, that looks a little funky. I'll just move it away. There we go. So, yeah. Acid, base, conjugate base. And then just to kind of help more with identifying Ks again for different reactions, there are two different ways you could find K for this one if like you wanted to. So you could either recognize that the acid that we would have a Ka for and water are on opposite sides. So that would be Kw over Ka of HCN. Because remember, when I have an acid going to its ions, it's normal Ka. But if I have an acid over on the product side, so if I like ions going to acid, that's going to be 1 over Ka. And then Kw goes with H2O becoming, it's the autoionization of water. So it'd be water going into its ions, hydrogen and OH. So this would be our Kw normal because it's water going to that thing. So you can either recognize that, or if that doesn't work for you, you can see that here we have OH. So we can see OH is a product. So that means it's a Kb, because remember, if I have a Ka, hydrogen's a product. So for Kb, OH is a product. And then Kb of what though? We have the Kb of our base of Cn minus, because it's what is going to accept that hydrogen. So Kb of Cn, but we don't have Kb of Cn. So that's equal to Kw over Ka of the conjugate acid. In this case, the conjugate acid, you add a hydrogen, so HCN, which we also identified here, the conjugate acid. So you can do it either way, you get the same answer. Just depends on how you like to look at these types of problems and what works for you. Yeah, so which of the following are true? True and false. We love true and false. For this one is both. And that is because the stronger the acid, the weaker the conjugate base. That is true. I like to think of it as like, this is my analogy where let's say I am an Olympic level figure skater. Like I'm a really strong figure skater. I'm probably going to be like weak doing something else, like basketball or something. I can't be strong with both. So that is a true statement. And then the stronger acid is always on the same side as the stronger base. Stronger acid with stronger base. It doesn't have to mean strong. They don't have to both, neither of them have to be actually strong. They just have to be stronger compared to the other side. So those are both true. Then, let's see. I'm so indecisive. It's just a color, Jordan. Just pick one. Okay. So for LiCl, this is aqueous. And it's also a strong electrolyte. Normally he would say that, but you guys are smart. You would know that anyway. So, for this, we have to break it up into pieces. So, we have Li plus and Cl minus. Actually, I'm going to put this over here so it's out of the way. The next one. Also, the 0.1 does not matter in this situation. So, Li plus is a group 1 alkaline metal. So it is neutral. We use those a lot, so you can either just know it, or you can see that the base of this would be LiOH, which is a strong base, which means it'd be a weak conjugate acid, which would lead to neutral. So you can think of it either way. And then for chlorine ion, the acid form would be HCl, which is a strong acid. So that conjugate base is weak, because remember, it can't be good at both things. So it's neutral. And a neutral plus a neutral equals neutral. Okay, I'm re-recording because I keep getting notifications. Okay, so this one's a little trickier. So we have CaSO4. So we have Ca2 plus and SO4 2 minus as our cation and anion. So Ca is a group 2 alkaline earth metal, which is neutral. You can either just know that because it's really common and we use it a lot, or you can recognize that CaOH2, and remember there's that 2 here because of that 2 up there we cross, is a strong base. Sorry if you can hear me like swallow. My ear, I still can't hear anything. So, strong base leads to weak conjugate acid, so that's neutral. Then we have SO4 2 minus. So a lot of times people want to go to H2SO4, but that's not right. That's not the next acid. We will only want to add 1 hydrogen, so HSO4 minus. I'll put it outside, not H2SO4, because we're only going to add 1. And H2SO4 is a strong acid, but HSO4 is weak. So this is a weak acid. So we'd have a strong conjugate base. Strong conjugate base. That means basic. A neutral plus a basic equals basic. And basic has a pH greater than 7. pH greater than 7. All right, next page. So, let's do another color. Okay, so if I have the pH of a 0.1 molar solution of KBRO, so now we're actually gonna like apply the math to this. So we could have like determined just in general that this would be a basic solution because this is neutral because it's group 1, and this is the conjugate base of a weak acid, so it'd be basic. So we could just tell that, or if they were like asking for it in general, but we're going to find the actual pH. So he kind of talked about it like if there's KBRO, then like K is neutral, and then BRO minus is our like conjugate base. So it'd be KB, which is then equal to KW over KA, because we don't have a KB for BRO minus bro. So it'd be KW over KA of HBRO. If that makes sense to you, because, and again, that's because KW equals KA times KB. If that makes sense to you, go with that. I'm going to explain real quick the actual reaction that's happening during this scenario, just so you can kind of get the full picture. So we have KBRO plus H2O, because we're making that solution, it's aqueous. And then we have like a double displacement reaction. So H2O can also be written like as HOH when I think of like double displacement. So basically our cations and anions switch partners. So now we have KOH and HBRO. And then we want to get our net ionic. So KBRO is going to split because it's a salt, strong electrolyte. So it's going to be K plus BRO. H2O stays together because it's a liquid. KOH is going to split because it is a strong base. I really hope you can't hear me swallowing. That'd be so awkward. HBRO is a weak acid. So it's going to stay together. So now we can cancel what we have the same on both sides. So that'll be K. So now we are left with BRO minus plus H2O yields OH minus plus HBRO. And then we'd have to recognize what the K value is. Sorry, I'm going to do like a bunch of different colors. So K for this, you could either see it as, kind of like we did on the first page, we have a water and our acid not on the same side. Water, which would then go to its ions, so water's on that side as a reactant, so it'd be KW, and then our acid is on our product side instead of our reactant side, so it'd be 1 over the Ka of HBRO, and then we add those reactions together, so it'd be over the Ka of HBRO, which is the same as what he said before. So if you wanted, like, again, if this works for you, dope. Or now that you like see this reaction and like you understand what's happening and now you can do this, cool, whatever. Hopefully something that I'm doing is helping. Even if you like don't do all this, maybe this helps you explain why this happened, why you do this, or if you want to do this out because it makes sense to you, whatever you want to do. You know me, I'm not picky as long as you have something you feel comfortable doing. So then we do like our rice table. I don't know, I'm running out of purples. So 0.1 molar solution of KBRO. So 0.1, it's going to be like a makeshift because I don't have room. So, well, I'll do rye. I don't need the change right now. 0, 0. And then we're still going to have basically 0.1 x, x. And then we're going to have that KW over Ka of HBRO is then going to equal, those colors are really similar to each other, and that's going to equal our x squared over 0.1. So then you would multiply by 0.1, square root it. X would then equal our OH concentration. So we take the negative log of our X of our OH concentration, that would get us POH. And then 14 minus POH equals our pH. That's how you do that one. And then for this next one, it's going to be essentially the same exact process. We'll do pink this time. What pink's the most tolerable for you guys? This one? So, again, you could also recognize that this one's going to be basic because we have a neutral and plus the conjugate base of a weak acid, so weak acid strong conjugate base, so basic. when I like post these like the actual worksheets for these, I'll do the math out. I just don't want to waste time while I'm recording. But anyway, so we have the 0.4 molar solution of LiF, so it's essentially the same thing. So we have that Kb of F minus is going to equal our Kw over our Ka of HF. If you want to skip through this next part, skip through. This is the reaction that's happening. We have LiF plus H2O, which is also written like HOH. And then we do the double displacement, where we switch anions and cations, and we get HF plus LiOH. And then we're going to split this, keep this together because it's water, keep this together because it's a weak acid, split this because it is a strong base, and we're going to have Li plus, and this one's got split because it is a strong electrolyte, plus H2O yields HF plus Li plus OH. Cancels out the same on both sides. Sorry guys, had a cough. Pause. We're back. Okay. Li we got rid of. So now we're left with F minus plus H2O yields HF plus OH minus. So then we can recognize that that is, again, Kw or Ka of HF, because water's on our reactant side, acid's on the product side. So again, you'd get Kw over Ka of HF, which we already talked about. So again, you want to skip all that. That's really fine as long as you understand it. And then we'll do our makeshift rice table. Just want to do rye. H2O doesn't matter because it's a liquid. 0.4, essentially 0.4, 0, 0, x, x. So that's going to equal our x squared over 0.4. X is going to equal our OH concentration. That's because it's our OH concentration. Oh my gosh, I don't know. I feel like Jay Shore. This is... I'm not thinking. Okay, anyway. So negative log of OH equals our POH. Then pH plus POH equals 14. So 14 minus our POH will equal pH again. So again, same thing as this last one. I just want to hit it with you guys again. Okay. Okay, and I'm back. Okay. So for this one, we just have to be able to identify, for this, we have to identify which side is stronger and which side is weaker. So for this one, we have NH4 plus Cl minus, NH3, and HCl. So I already do a scan of those, and the only one that is a known strong is HCl. It is a strong acid. So this is our strong side. Strong side. However, we have more of the weak stuff at equilibrium. And that's because, like, let's say if I had like HCl strong, we would mostly have ions at equilibrium, not the thing that's strong. So we mostly have what's weak at equilibrium, which is our reactants. So we'd have more reactants at equilibrium. So we already know that these two are wrong because we have more reactants at equilibrium. And K is equal to products over reactants. So if I have more reactants at equilibrium, it's going to be 1 over, or it's going to be K is less than 1, because it's going to be like a fraction. So we then know that the answer is K is less than 1 and more reactants at equilibrium. Okay, I'm back, y'all. Okay, so for this one, we could go through and see if there's anything that we could get rid of to make like a net ionic equation and get rid of spectator ions. However, we have HF, which is a weak acid, so it's going to stay together. BRO is it's a polyatomic ion that's going to stay together. HBro is also a weak acid, so it stays together, and then F. So we already have our net ionic. There are no spectator ions for us to get rid of, so we have that established. So now I see I have HF and I have HBRO. Oh no, 5%. Okay, we're chilling. Okay, it's fine. As acids that we have like K's for. So I recognize that we have HF going to its ions, so that'd be normal Ka of HF. And then I have HBRO on the product side, which would then go to its ions. So that's 1 over the Ka of HBro. So I'm combining those two reactions. So if I drew it all out, or wrote it all out, it'd be HF yields H plus F minus, and then H plus BRO minus yields HBro. Add them together. H's go away because they're the same on both sides. HF plus BRO minus yields F minus plus HBro. F minus plus HBro. So it's same thing. Add those two reactions. This is normal K. Oh, sorry. This is normal Ka. This is 1 over Ka, because here it's acid to ions and here it's ions to acid. So what happens when we add a reaction together? We multiply the K's. So if we multiply those K's, we get Ka of HF divided by Ka of HBro. Yay. Okay, for the next one, okay, now we'll do like green or something. Did I do green in the last bit? Yeah, I did. Okay. Which of the following, for the following reaction, NaF plus H2O yields NaOH plus HF, all aqueous. What is the K? So we have NaF, which is going to, here, I'll just write it again. H2O yields NaOH plus HF. This is going to split because it's a salt. H2O stays together. Oh, and then salts are strong electrolytes. NaOH is a strong base, so it's also a strong electrolyte, will split. And HF is a weak acid, so it's going to stay together. This is a base because it has OH. This is an acid because it has hydrogen. So I have Na plus F plus H2O yields Na plus OH minus plus HF. Cancel what's the same on both sides, so get rid of those spectator ions, Na. And we are left with the net ionic of F minus plus H2O yields OH minus plus HF. And that is equal, our Kw would then be Kw over Ka of HF. And you can either recognize that because we have the water and the acid on not the same side. H2O going to its ions is normal Kw versus ions to an acid is 1 over Ka. Or you can see that OH is a product, so it'd be Kb, but we don't have a Kb of F minus, so it'd have to be the Kb would equal Kw over Ka of the conjugate acid, which is in this case is HF. So same thing, depending on how you want to think of it. So that is their K. What is more present at equilibrium, products or reactants? So here we could also, if I actually did the whole K out, like if I did the math for it, I could determine if it was greater than 1 or less than 1. But I don't know that, so I'm just gonna look at this kind of like the way we did this one. We identified which side was stronger and weaker. So here, let me zoom. Okay, so here I see that we have a strong base here. So because this is a strong base, It doesn't matter that this isn't a strong acid. This is still our stronger side. So this is our stronger side, and then what do we have more of at equilibrium? We have more of the weak stuff. More of the weak stuff at equilibrium. So again, we have more, oh, the green highlighter is so ugly. We have more reactants present at equilibrium. And then that is associated with delta G being positive. Those greens look so ugly together, it's fine. And it being non-spontaneous. So that's a good time to review all of those things. Maybe I'll put it off to the side over here. Why can't I just pick a color? Okay. Let's say we have K is greater than 1 versus K is less than 1. Is that an okay color for you guys to see? I feel like it's kind of harsh. Maybe we'll do this. Sorry, I don't mean to be picky. No, it looks too similar. Okay, whatever. It's fine. It's fine, Jordan. Okay. K is greater than 1. Then we have more products at equilibrium versus K is less than 1. We have more reactants at equilibrium. So that means delta G is negative versus delta G is positive. This is spontaneous. This is non-spontaneous. Products are more stable. Reactants more stable. Because we'll have whatever's more stable is like more present at equilibrium. Because we all want to be more stable. And then this relates back to the pick me girl analogy, where if I have the products are more stable, that means that it has lower potential energy, so the reactants have higher chemical potential energy. Versus here we have products have more chemical potential. Sorry, I got a little tripped up. I just get the dumbest notifications on my iPad and it throws me off. Okay, so we know that to be true. Oh, why did... Whatever, it's meant to be. Okay. And then we'll do this one real quick. Light blue. Okay, so here we have HCl. Maybe write it. Maybe I'll do it up here. I have HCl plus NaOH yields H2O plus NaCl. So let's get rid of spectator ions. So HCl is strong, so it's going to split. NaOH is strong, so it's going to split. H2O stays together. And NaCl is going to split because it is a salt and a strong electrolyte. They're all strong strong acid, strong electrolyte, strong base, strong electrolyte, salt, strong electrolyte. So we have H plus Cl minus plus Na plus OH yields H2O plus Na plus Cl minus. A lot of things on there. So now I can cross out chlorine and Na. And what am I left with? Oh my gosh, H plus OH minus yields H2O, and that's it, which is our 1 over our Kw of H2O. So I know that is then, well, if Kw is 10 to the negative 14th, this will be, that's K is less than 1. So this is going to be K is greater than 1. So if K is greater than 1, we have, sorry, I guess I gotta finish this one too. It's positive. Okay. Then K is greater than 1, so if K is greater than 1, we have products more at equilibrium because it's products over reactants. That will give us our K is greater than 1. Delta G is negative, and that is spontaneous. So, hopefully that helps a little bit. If it wants to zoom out for me, hopefully that helps you guys. I'll still post this, and I'll run through the math for all of it real quick, and then put the math in here to submit. And otherwise, I hope that helps. If not, email me. I seriously care about you guys so much. I want you guys to succeed and do well and feel confident in yourselves. So much. And I hope you know that. Otherwise, yeah, I hope you guys have a wonderful rest of your day, evening, morning, whatever time it is when you're watching this. And yeah. Alright guys, I will see you later in tutoring. Bye.